All right. So, ionic compounds, we've said that you can tell an ionic compound because it contains a metal. But there's a better definition for an ionic compound. And the best definition of an ionic compound, unfortunately, is not very descriptive of what it is, but it's a compound that's made of ions. A compound made of ions. Now, you know that ions are when there's an imbalance of the number of electrons and protons. So they're particles with charges, but whether it's atoms, or sometimes we have something that are called polyatomic ions, many atoms that come together to form these ions. So we'll talk about that in the future as well. But if you take a salt and you put it into water, you will add conductivity to the water because of the resulting ions that occur when a salt is placed in water. Okay? Now, conductivity isn't saying that the ion is creating electricity. What's going on is the ions are facilitating the movement of the current of electrons from one side of an electrode to another. So to create light from the light bulb, you need to have a power source like a battery. But then there's a break in your connection here, and the salt water allows conductivity to electricity to conduct through the salt water. Pure water, conductivity will not flow. If it's just powdered salt, just solid salt, sodium chloride or any other kind of ionic compound, because remember, salt is not just sodium chloride. Salt is any kind of ionic compound. Ionic compounds are not conductive. However, if you dissolve them in water, they will be, or if you make them into a liquid by heating them up, then they will become conductive as well. So, ionic compounds, compounds that contain metals, compounds that are made of ions, molecular compounds, compounds that are made only of nonmetals. Okay? So, I have my periodic table here. Let me bring it up really quick. Show us our nonmetals, these ones over here, and hydrogen, right? Because that is our way of identifying whether a compound is a nonmetal or not. Okay, so moleculars are made of nonmetals, so it's molecular. Okay, so this slide here, remember this slide?
Oh yeah, I remember this slide.
It's a good one, huh?
Yeah, it's a good one. It's fun. It's easy. I like it.
All right, well, let's see if it's still easy for you. So, everybody at home, go identify the number of protons, neutrons, and electrons, and then come back and see if we get them right together. All right, Fred, what did you find?
For cobalt, I see cobalt is number 27, so there's 27 protons.
Good. And neutrons?
Let's see, it's 33 because 60 minus the 27 is the neutrons. 60 is the sum of the protons and the neutrons.
Very good. How about electrons?
Well, if there is no charge, there'd be 27. But this has a +3 charge. That means that we gain 3 protons, therefore...
No, we didn't gain 3 protons. We did what there?
Oh yeah, you don't gain protons, you lose electrons. We lost 3 electrons. That means there's 24.
Very good, 24 electrons. 24 electrons, excellent. So, bromine 81, how many protons?
35.
And neutrons?
46.
And electrons?
Well, there's 35, but there's one more because there's a negative charge, so 36.
Excellent. And what is this?
29, that's copper. 36 plus the 29, that's 65, copper 65. 27 electrons, though, that means 2 extra protons. It's with a +2 charge.
Very good. Excellent job. Okay, so we can also use the periodic table and know where or what kinds of ions elements will want to form. So for example, by looking at the location of bromine here, Br, I can look at the number of electrons it has. How many is it?
35.
And then see the closest noble gas,
36.
and know that bromine wants to gain 1 electron. And because of that, everything in this column is going to want to form a -1 charge when it forms an ionic compound. Everything in this column is going to want to have what kind of a charge?
I don't know. How do you know that?
Well, here's sulfur. We can look at how many electrons it has,
16.
and we can see the closest nearest gas, noble gas, is 2 electrons more. So it's going to want to do what?
Gain 2 electrons?
That's right. So that's why oxygen, sulfur, and selenium want to have a +2 charge when they form ionic compounds. We can do the same thing over here. Sodium, what does it want to do? What did we say?
Well, I guess if it gained 7 electrons, it could become like argon.
Yeah, but gaining 7 is harder than just losing 1.
Oh, yeah.
So if it just loses 1, it has a noble gas electron configuration of neon. Okay? So all the elements in this column behave the same way. They all want to lose 1 electron when they form ionic compounds. And this column here, look at calcium. What would it like to do?
It's going to want to lose 2.
That's right, because it's got 20, and whose electron configuration is it going to want to be like?
Argon, by losing 2 electrons.
Very good. Excellent job. So we can use our periodic table to answer what is the expected charge on calcium.
+2.
That's right. Here it is, +2 charge. How about sodium?
+1.
Very good. It's at 11 here, and it's going to want to have 10 electrons to have an electron configuration similar to that of neon. How about nitrogen? What is it going to want to do? Here's nitrogen here.
Will nitrogen gain 3?
That's right. Nitrogen will have gain 3, and what kind of a charge does that make on it?
A -3.
Very good. And oxygen?
-2.
Excellent job. Okay, so when we write these ionic compounds, remember that we want to bring the metals and the nonmetals together in such a way that the number of electrons that the metals lost is the same as the number of electrons that the nonmetals gained. Okay? So if I have my ions already sorted out and I want to form compounds between them, then how many of these aluminum ions and how many of these oxide ions are going to come together? What's their ratio going to be?
Let's see. If I have one with a +3 charge and one with a -2 charge, I'm going to need more negative charge.
Like that?
Yeah, but when I do that, I'm going to need more positive charge.
That's too much now, huh?
Yeah, now I need more negative, but that's the right number right there, because now I've lost 6 electrons from the aluminums, and I've gained 6 electrons by the oxygens.
Very good. So from this, we see that we're going to need the resulting compound is going to be Al2O3. Okay, can you see that? And we would write that 2 of these aluminum ions are coming together with 3 of these oxide ions, -2 charge, to form an Al2O3, aluminum oxide. Very good. Another thing that we can do is we can use this thing that we would call the crisscross rule. We just look at the charge on the elements, the ions, and see how those numbers end up being related to the number of atoms of the opposite, or the counter ion, the other ion. All right. So with that in mind, we can do the same thing with magnesium and oxygen, but we only state the simplest whole number ratio, so we wouldn't say Mg2O2. Because when these ionic compounds come together, they are coming together into what we call, these ions are coming together in 3-dimensional lattices, like this. So this is a chloride ion, and the white ones are sodium ions, okay? And then you have, whoops, I paused them there. Then you have these 3-dimensional lattices. So in reality, a piece of salt has, millions of sodium ions and chloride ions, but we only need to say what the ratio is, okay? So we always report it in the simplest whole number ratio because these ionic compounds come together in these three-dimensional lattices. You have to start remembering that phrase, three-dimensional lattice, and always thinking about ionic compounds in that way. Okay, so now we have this thing. Remember I referred a while back to polyatomic ions? Polyatomic ions? Well, here we have polyatomic ions, a cluster of atoms all coming together, and they have a charge after they've come together. Well, we can do the same thing with the crisscross rule. We can see that we need 3 of these NH4 pluses for every 1 of these PO43 minuses. So we write that with our parentheses like this, and the 3 goes here, indicating that we have 3 of these for every 1 of those. Okay, good job. So, work on this one at home. Identify what the correct chemical formula is for this combination of potassium ions and oxide ions. All right, did you get to work on it? If you didn't, push pause and do it. Fred's going to talk. We're going to talk through this one with Fred.
Can I see the periodic table?
All right. Potassium ion. Where's it at? Where's it at?
There it is, right there. So it wants to form a +1 charge.
How did you know that?
Because it has 19 electrons and it can get 18 if it loses one. So it's going to have a +1 charge when it loses an electron.
Very good. And what is oxygen going to do?
-2 electrons, or -2 charge.
That's right. It's going to gain 2 electrons and get a -2 charge. Okay? So it's important that we say that correctly. Now, after we write that down, we can see pretty clearly what's going to happen, right? We can use our crisscross rule, and which one of these is going to be the right answer?
C.
That's right. K2O1. And again, what that's saying is I need 2 of these positively charged potassiums for every 1 of my oxygen that has a -2 charge. Okay, very good. Now, we can look at the elements that are metals here in these first 2 rows are representative metals, and aluminum also, and gallium. But when we start looking at these elements down here and some of these over in this area, we call these transition metals and post-transition metals. When we start looking at those, what happens is we find that there are multiple charged states or multiple charged species of these transition metals. They don't follow the rules the way that we've presented them so far, so they aren't representative elements. Only our representative metals really can predict, just simply by looking at the periodic table, what kind of ions they'll form. But our transition metals oftentimes will form multiple kinds of ions. And so we have a different way of naming ionic compounds that contain transition metals. Okay? And this is what we do. If it contains a transition metal, then we use a Roman numeral to help the person reading or seeing the name of the compound know what the charge is on that transition metal. Okay? So, for example, if I have a compound like this, FeS, Fe, do you know what Fe is?
Iron.
And S?
Sulfur.
So we have iron sulfide. All of these are different forms of iron sulfide. Okay? But iron can form a +2 charge or it can form a +3 charge. And so we're trying to find out what forms when you have an iron with a +3 charge. Okay? And if you were to take iron with a +3 charge, how would it come together with the sulfide ion? So, go ahead and take a chance at home to try to find the answer to this one, and then come back and Fred will help us out. Okay, did you take that chance? So, the sulfide ion, Fred, what is the charge on the sulfide ion?
Where is it at?
It's over here, number 16.
16 electrons. It wants to gain 2 to become like argon, so that's a -2 charge.
Very good. So it's a -2 charge. So now we have iron 3 and a sulfur with a -2 charge. That's going to be Fe2S3, right?
Yeah, that's right.
So our answer is C. But the question also we want to know here is, what is the name of that compound? The name of this compound?
Iron sulfide?
Okay, it's iron sulfide, but because iron is a transition metal, I'll bring in the periodic table here so we can see where it's at. Iron's a transition metal, and that's our rule. If it's a transition metal, we recognize that it might have more than one way of forming an ion, and so we're going to name it to help people know what kind of ion it formed. And we're going to call the compound either iron 2 sulfide or iron 3 sulfide based on the charge that is on those iron ions. Okay? So because this is iron with a +3 charge, then this compound, Fe2S3, is going to be called iron 3 sulfide. That 3, again, tells us the charge on the iron ion. Okay, very good.